Okay, I'm going to start talking about central auditory processing. We've talked about the ear and the inner ear and how sound is transduced, and now we want to get this information to the brain and to higher level processing. Okay, I usually start with the verbiage, and I'm going to try to start with the picture because I usually talk better from the picture, and then we'll go through this with the words on the slides. But so if you notice the cochlea, what we were looking at as the seashell type thing that is in the inner ear, that you can kind of see pretty well in this picture, with the outside of that, the semicircular canals that is our vestibular, part of our vestibular system. But that cochlea is going to, so that's where the inner hair cells are communicating to the auditory nerve, and the auditory nerve is going to take that information into the cochlear nucleus in the brainstem. And so that's, I hope, easy to remember because we've gone from the cochlea to the cochlear nucleus. And then that brings the information up to the superior olivary nucleus, or the nuclei, as they're both on both sides. All of these structures are bilateral on both sides of the brain. And you can see in this picture that there is some crosstalk. So there's quite a bit of contralateral communication, but there's also ipsilateral communication, so information going up the same side. But as I'm going to show you at the next picture slide, most of it is contralateral, so it's crossing over to the other side of the brain. So when I'm hearing a sound in my right ear, only that is then going to travel over to the left hemisphere. I'm listening to a sound right now called someone's motorcycle, I think. So up to the superior olivary nucleus, up then to that communicates to the inferior colliculus. And there's some crosstalk there again between the inferior colliculus, actually, and the medial geniculate nucleus. If those start to sound familiar, so for hearing, that cochlear nucleus and the superior olivary complex, those are in the midbrain, which allow us that nice reactive kind of when we hear something loud and sudden, that we have a really quick response to that. We're going to communicate that up to the midbrain tectum, where the inferior colliculus might sound a little bit like superior colliculus that we saw for vision. Remember, information for vision was split between the superior colliculus and the lateral geniculate nucleus, but here we're going to take it all through the inferior colliculus, but again in that midbrain, so it's inferior just below the superior colliculus. This is for hearing, and then take that information from the inferior colliculus to the medial geniculate nucleus in the thalamus. And again, that should sound familiar, right? Because it's kind of similar sounding to the lateral geniculate nucleus. This is just another thalamic nucleus, another nucleus in the thalamus, more medial, more midline in the brain than the lateral geniculate nucleus. And then we're going to take that information up to the auditory cortex, or the primary auditory cortex and the temporal lobes. So I'm going to repeat that with the words on the slides, as I think pictures help us to see, and it helps me to talk from them, but I think all of us kind of want the words on the slides when we're taking notes. Although remember, you can print these up 3 to a slide and take notes that way too. But the cochlea, we have information leaving via the auditory nerve. So we have those inner hair cells communicating to the auditory nerve. It takes that information to the cochlear nucleus in the brainstem. And then that information goes to the superior olivary nucleus in the brainstem. And remember, that's where we had that contralateral communication. And ipsilateral communication. What this allows for is this is the first place where we're going to see convergence of the information from the two ears, from both ears. So we're going to see that this is involved in sound localization. We use these cues that are differences that are happening between the two ears to tell us about where sounds are coming from. Information gets sent to the inferior colliculus in the midbrain. So when I was in school, this is where we talked about that sound localization mostly occurring. And my understanding, okay, is that those animals like cats and bunnies that can move their ears, that their inferior colliculi are actually more complex than ours because they have to take in that information as well as which way are their ears pointing, just the same as we need to take in information about our eye movements, which they do too, but they have to take in that information of ear movements and which way are their ears pointing. But it looks like many mammals do a lot of this sound localization in the superior olive rather than the inferior colliculus, although we'll see some different studies. And then from the inferior colliculus, it's going to communicate to the medial geniculate nucleus in the thalamus, which is then going to take that information to the cortex, in this case the primary auditory cortex, called A1, just like we called the primary visual cortex V1, in the temporal lobes. And all of these are laid out in a tonotopic map. So I briefly introduced that idea when we talked about place theory and how the basilar membrane is really giving us this, it has a tonotopic map with low frequencies near the apex and high frequencies near the base, kind of backwards than the way that we think of when we look at the shell itself. But remember, the basilar membranes really moving its thicknesses and thinnesses are opposite of that cochlea. And we're going to keep that tonotopic map through all of these structures and through to the primary auditory cortex, which is also in a tonotopic map, where high frequencies are close to other high frequencies, low frequencies are farther away from them, and then low frequencies are close to other low frequencies. Try to make that as clear as possible. And so if all of this seems like a lot, and it kind of is, I mean, auditory information, not only is the ear really complicated in its own special ways, mechanisms of the ear, but then we have all this long pathway to finally get to the auditory cortex. You can remember the acronym sonic MG. I'm not really an acronym person myself, but this is a really helpful acronym for those middle ones. So remember the cochlear nucleus. I'm hoping that's an easy thing to remember because it's in from the cochlea, which we've talked about a bit. And the auditory cortex, when we get it to the cortex, again, I'm hoping that's pretty straightforward because it's going to be reminiscent of the visual cortex, and we're going to talk about that a bit. But these other structures all fit into sonic MG. So the superior olivary nucleus, SON, the inferior colliculus, IC, and the medial geniculate, MG. And so, especially if you're a car person, maybe you can just visualize the car, and that will remind you of the acronym. It really depends on how you learn. Okay, I'm going to talk from another picture, and this is not to give you more information to remember, because you don't have to remember anything from this that's different than any of the previous ones. I just feel like it shows better what's happening with the contralateral communication and ipsilateral communication. Okay, so this is kind of showing, I'm going to assume the brain's facing away from us, and that is the right cochlea communicating into the cochlear nucleus. You can see that on the same side there in the brainstem, which communicates over to the superior olivary nucleus. You can see the darker, more filled in lines going contralaterally, but also you can see coming from the cochlear nucleus a kind of light line, which is showing a secondary pathway coming to the ipsilateral to the superior olive on the same side. Okay, and then traveling up through the midbrain to the inferior colliculus. And again, because we're looking at just one ear, we can see that contralateral is the main pathway, and then the ipsilateral is the secondary pathway. And then between the inferior colliculus and the medial geniculate, we have more crosstalk. We're putting this information together again. And then the medial geniculate communicates out to the auditory cortex. And again, these are all laid out in a tonotopic map. And whether the going through the brains helps you or looking at the squares, that diagram helps you, it's just another way to visualize the information. Part 2 of this is the processing that is happening in the auditory cortex and beyond. So we're already getting our auditory information to higher level cortical processing. Happened much more quickly than it did for vision. We get to the core area, or A1, where information is first coming into the cortex. it is activated by simple sounds, so pure tones. It's going to be activated by more complex sounds, but it is responding to those pure tones. And so it's kind of like what we saw in V1, that it's responding to the features of the environment. And we're going to take these, just like we took different lines of different orientation and moving lines, and we put them back together into something meaningful. We're going to take this pure tone information and put it back into something meaningful. It's really quite incredible, everything that the brain goes through just to process something like me speaking. And again, as I've said now a couple times, with all of those structures in between, the auditory cortex as well has a tonotopic map where neurons are laid out in order of response to frequency. And this has an attempt to show how we have those low frequencies. So the reds and yellows are close together, middle frequencies, and then we get into high frequencies, which they're representing with indigo violet. And you can see those indigo violet, we have those close together, and it goes kind of a little bit back and forth, at least according to this model. From the auditory cortex, in that core area, we are going to move to the belt and parabelt areas for higher visual processing. And you can kind of think of that core area outside of A1 that it's pointing to, kind of like the extra striate, V2, but in some of those pathways that we have to go through for either the what or the where. But then we're going to move to the belt and the parabelt area, where the neurons are now requiring increasingly complicated stimuli in order to activate those neurons. So complex tones, complex sounds, speech, animal sounds, ringings of telephones, etc. And if we think of A1 as being similar to V1, like I was just saying, that we've split these features, we've split the world into features, we need to put that back together. These areas of higher processing are also going to have a similarity to those in vision, where they require this a complex stimulus in order to activate. And we see these kind of modules. So when I was in sensation and perception, I took the advanced sensation and perception because I really liked it, and we read about people with some specific brain damage. And I remember there was one article about a man who was lacking the ability to hear the difference between different kinds of rings, like whether, and these were really wide ranging, if I remember correctly. This was about 30 years ago, but I read this, but telephone ring, the train whistle, a dinging of the bell when you go to the hotel or whatever we see on movies. I can't think of all the different bells that exist in the world, but all those things that kind of fit into the category of bell, that module, that he had damage to that. But he could recognize, animal sounds and speech and music and all of that. So similar to the fusiform face area, the extrastriate body area, or the parahippocampal place area. And so as I started to say, with that brain on there, but not really clearly because I knew I had a slide, I was going to talk about this, as we get beyond the auditory cortex, just like with the visual cortex, sending that information on into these two streams, the what stream, the ventral stream that's helping us to identify objects, sound objects in this case, like birds or music or me speaking, and the where stream, or the dorsal stream going up through the parietal lobes, where we localize sounds. And just like we saw in vision, where with the neuropsychological evidence that we see a double dissociation between the what and the where streams, that we can damage one and have the other one maintained, or we can damage the other and have the one maintained, which suggests that they are truly independent of one another, which is not to say that those of us who are, quote, normal without damage, that those areas aren't communicating, but just that we can do one task without being able to do the other. So JG has damage to his ventral pathway. If I'm remembering these two people correctly, I think JG is a he and ES is a she, but I might be mixing them up. JG has damage to his ventral pathway, so he cannot identify sounds very well. He can localize sounds, but is poor at identifying, and you can see his performance over there in the left part of that graph. ES has damage to her dorsal pathway, and she can identify sounds just fine, but she's poor at localizing where sounds are coming from. You can see where her damage is over on the right, and then her performance on these different tests of localization and recognition. Finally, I'm going to talk about plasticity again, which we did in the visual realm when I talked about the Greeble study, one of my favorite studies, because the Greebles are just, they have a great name, and it's a cute study. And because we see this plasticity, that we see this change in the brain and its function based on a specific experience. And in that study, it was just a week or so of training. It was just, I can't remember if it was 4 or 7 hours of training, but it wasn't very long before we see a change in the function of that structure and what it's responding to. In the case of the auditory cortex, they have looked at owl monkeys, where they have played, and I might forget some of these numbers. I was going to go get my book, but I figure it's going to be okay just because my numbers are off. It's going to be okay. So they gave the owl monkeys something like a 2500 hertz tone, so a pretty high-pitched tone, boop, up there, and they trained it to discriminate between that and a tone that was very close to that, which I'm not going to try and do right now. But for one of those tones, they wanted to perform a task, and for the other tone, they did not want to perform the task, and that's how they got rewards, if I'm remembering the study correctly. And what they saw in the auditory cortex was, before training, it had this kind of mapping where that auditory cortex was responding to a 2500 hertz tone in a similar way as it was to the 4000 or the 3000 or the 2000 or the 1000 hertz, as they tested these different frequencies. And then they went back and tested after training, and that place that was responding to 2500 hertz specifically had basically grown into those other areas and around, so that more of the auditory cortex was responding to that specific tone that they had been trained on. Pantev et al., Chris Pantev and his colleagues, have looked at musical training, and they see that people with musical training have enlarged parts of their cortex that are responding specifically to piano tones. Their cortex is not necessarily responding, there's not a larger part responding to non-musical sounds, but when they tested piano tones, they see more of the cortex is responding. And they see, again, response to music. Electrical activity was twice as strong for musicians as for non-musicians. So I had already clicked off when I realized I want to say one more thing about plasticity and the brain. So I've read a book called The Brain That Changes Itself, and I think it's really important to remember that our experience can change, not the overall architecture or settings of our brain or anything, but how those particular areas of the brain function and what they respond to. And I think it's interesting, and I also think it's helpful for those of us who struggle and have some amount of issues with their brains, as my family has a pretty weak cerebellum. Most of us have weak cerebellums, so I think it's just a good thing to remember for those of you who struggle at all, that it's worth sometimes putting in the work and practicing to develop those areas of your brain. And practicing music can do some interesting things from what the research appears to show. But anyway, the last part of this central auditory processing is to discuss pitch and the brain, or the cortical processing of pitch. If you remember, we've talked about the coding of pitch before, really at the level of the basilar membrane, that we have place theory, that it is we have maximal displacement at a certain place that's going to tell us about pitch. and that we have the phase locking, the temporal coding for those pitches lower than about 4,000 hertz to help code for pitch as well. So we end out in the auditory cortex with this three-dimensional tonotopic organization for according to frequencies. And Bendor and Wang asked the question of how can we be sure that these neurons are actually responsible for pitch per se, because remember, I'm going to take you back to the very first talks on sound, that if we pull out the fundamental frequency, that we are still perceiving the fundamental frequency as long as that fundamental frequency is being maintained in the difference of whatever frequencies, right? So I have an example here to kind of walk you back through it, but Bendor and Wang recorded from neurons that respond similarly to complex tones that had the same fundamental frequency. So regardless of the harmonics and how we are getting at that perception of that fundamental frequency, that's what they're measuring. And they called them pitch neurons because they actually existed. And I think it's pretty amazing. And so I'm using a different number than he uses in the book because 186 is hard to, 182 is difficult to multiply out, even though I think he might even have 3 examples. But I wanted 3 examples with my fourth. So I'm looking at the neural response of this particular pitch neuron, as we're going to call it. And just so I'm going to start out by saying it responds to 220 hertz, that pure tone. We're in the auditory cortex, it responds to pure tones. Okay. It also responds, so this is, if you kind of want to go, that's a little bit confusing. It is. It also responds to when I have 220, 440, and 660 hertz. Remember, with those harmonics, we're going to still hear that as a 220 hertz tone. That pitch neuron is going to respond. If we have 880, which is a multiple of 220, 110, which is 880 plus 220, and 1320, if we have those 3 harmonics, okay, 220 is not even in there anymore, but remember, we're going to perceive that as being a 220 hertz tone. That is actually mind-blowing in my mind. We're getting up into those higher frequencies, but as long as that 220 is maintained in those differences, we perceive 220. And yes, the pitch neuron responds. I'm going to move up one more section because I think he actually moves up into up to 2500. But so this happens. So we have these higher frequencies, 1540, which is a multiple of 220, 1760, which is 1540 plus 220, 1980, which is 1760 plus 220, if I've done all my math right. So I'm maintaining that 220 in those differences and in how it's multiplied out, but 220 hertz is no longer part of the stimulus itself, but I'm going to perceive that as 220 and yet 220 hertz, and yes, that pitch neuron has a neural response to those 3. But give it 1540 on its own, no, it doesn't respond to that. Give it 1980 on its own, no, it doesn't respond to that. This is a pitch neuron that responds to 220 hertz. Okay, again, regardless of how I get there. So that's the end of this. I'm going to go ahead and do my little bit of summary here. So that's the end of the central auditory processing. I think I'm going to move on to sound localization, but I find it ends on a fascinating study. I hope sometimes that you guys are as mind blown by it all as I am, because I still don't even, part of me doesn't believe it, but I know that it's true. So, okay, I'm going to finish up with localization next.